It's my pleasure to welcome you on the second virtual panel on hardware security. The specific topic is side channel leakage. Can CAD come to rescue? I'm Saurabh Vunia. I'm professor at University of Florida. It's my pleasure to welcome you on behalf of the organizing team, Dr. Gang Q, Dr. Sung E Ho, and Dr. E Jin, who are all here. And we'll be having an exciting panel today. We have a distinguished set of panelists. I'm very privileged to welcome them also here. I'm also very privileged to welcome Dr. Patrick Schaumont. He's a professor at WPI, one of the pioneering figures in the field of hardware security. He has made significant contributions in many different aspects of hardware security, including, of course, side channel leakage. So we'll start the panel right now, but before that, I would like to talk briefly about the CAD for Assurance initiative, which we took several months ago, to be precise, October 2021, during the pandemic. Group of members from the hardware security community wanted to come up with an initiative where we can assemble the CAD tools, benchmarks, and metrics for hardware assurance in one place, and that's when we created the CAD for Assurance website. We also started a number of activities, including tool demo and webinars, as well as a series of virtual panels, and this is the second in that series, and there will be more coming. There will be the next one on security verification in about a month. So every month we have one such event happening, and you can see the information in IEEE CEDA website as well as CAD for Assurance website. We are also very proud to have a group of sponsors for these events. IEEE CEDA, we are very proud to have that as a sponsor. IEEE Hardware Security Technical Council as a sponsor, and UF, University of Florida Woudenberg Institute as one of the organizational sponsors. In terms of technical sponsors, we are also pleased to have Alien, Mercury, Northrop Grumman, who are also sponsoring these events. And last but not the least, we would like to acknowledge continuous and high quality support from Amanda Osborne from IEEE CEDA. Really appreciate that, Amanda. Thanks a lot. With that, I will hand over to Patrick. Hopefully you will enjoy the panel, and we'll basically encourage you to participate in the panel by asking questions or providing comments. Thank you. Over to Patrick.
Thank you very much, Swaroop. Good morning, everybody. I'm going to switch the slide deck to the following slides. All right. Will the slides come up? Okay. So good morning, everybody. So welcome to the panel, Side Channel Leakage, Can CAD Come to the Rescue? We have a great set of panelists who I will be introducing in a moment. I will first briefly summarize the problem that we are going to discuss today. So imagine that you are a designer and that you are designing an application for a complex system on chip. And let's for a moment assume that you're writing this software crypto.c. And you want to know, of course, whether your crypto.c is correct, so whether it will provide all the information assurance that you hope that algorithm promises you. Now, the way cryptographers develop these algorithms is they think of this as a black box. They think that once your algorithm is designed and programmed into your chip, it will operate in a completely isolated box, and it will talk to another completely isolated box. So really all that you have to deal with is data in flight. And under that assumption, your algorithms are protected by computational security. And so it's up to the cryptographers to make sure that these algorithms work. The reality, of course, is not like that. What we found out in the past 2 decades is that these chips, they're not black boxes, but they're gray boxes. And depending on the capabilities of the designer, as the cryptographic operations execute on that system on chip, these operations, they consume energy, they take time, and these operations can be observed by other means. Depending on the level of abstraction that the attacker is able to observe, the attacker may be able to observe timing at high abstraction level, or it may be going to very deep levels of, or very low to the physics levels of abstraction, such as EM emissions or optical. And so then the question is, how do we deal with this problem? And how can we help the crypto application developer give an assurance that this type of effect, which is actually never taken into account during the development of the algorithm, can be dealt with? And there are really two flavors of this problem. The first flavor is that of the post-silicon side channel leakage characterization. And for that, you have to imagine you're an application developer that develops for an existing chip, such as a system on chip or an FPGA or a microcontroller. The problem in that case is that you don't have the detailed design data available for these chips. And as such, explaining the root cause of side channel leakage effects becomes extremely hard. In addition, there is not really any CAD available. The vendors will provide you with development environments, but they're currently, apart from the academic community where there is work, there are no commercial tools available to help you address that effectively. Secondly, the second flavor of that problem is related to the pre-silicon characterization. And in that case, you're looking at the designer who is designing a chip from scratch. There, the problem is that you do not have the physical artifact available of your chip. And as a result, you have to choose how you're going to model side channel leakage. How do you model power? How do you model electromagnetic emissions or even optical effects? And once you understand how they are created, how can you fix it? Again, you have the same question there. Where is the CAD? We have plenty of tools available that help us to provide design closure, that help us optimize timing or power. We don't have design tools available that help us fix side channel leakage automatically, apart from, again, academic efforts. And so this panel will address this problem. Can CAD come to the rescue? I will now introduce the panelists, and I apologize beforehand of giving you a very brief introduction. We have a very illustrious set of panelists, and you will hear from them in a moment. So first up, we have Mr. Serge Leef. Serge Leef joined DARPA in August 2018 as a DARPA program manager in the Microsystems Technology Office. His research interests include computer architecture, simulation synthesis, semiconductor IP, cyber-physical modeling, distributed systems, secure design flows, and supply chain management. He is also interested in the facilitation of startup ecosystems and business aspects of technology. Mr. Serge Leef manages numerous DARPA programs in the area of secure design automation. Next, we have Jasper van Woudenberg, who is the Chief Technology Officer of Riscure North America, located in San Francisco. Jasper is the Principal Security Analyst and ultimately responsible for Riscure North America's technical and innovation activities. Jasper has spoken at many security conferences and has given invited talks at Stanford, NPS, GMU, and the University of Amsterdam. Next, we have Colin O'Flynn. Colin O'Flynn is the Chief Executive Officer of a startup company called NewAE Technology, located in Halifax. NewAE is well known for their Chip Whisperer project and now also Chip Whisperer Chip Shouter project, which is a low-cost and open source tool chain that makes learning about side channel attacks easy and affordable. Colin regularly contributes to hardware security conferences by giving tutorials. And last, we have Francesco Regazzoni. Francesco is a professor at the University of Amsterdam, as well as a senior researcher at Alari Institute at the University of Lugano. His research interests include side channel attacks, cryptographic hardware, and EDA for security. Francisco has been a visiting researcher at NEC Labs America, RU Bochum, EPFL, and NTU Singapore. The panelists will give their opening statements in a moment. And so to structure the discussion, I've given the panelists 3 opening questions. After the opening questions, after the opening statements, we will open the floor for questions. I encourage all the participants as well as the panelists to make this an interactive panel. Really, the learning will be in the discussion that we have on talking about CAT4 side channel leakage. The first question is related to side channel sign-off. If you look at modern CAD, you have these sign-off flows where designs are automatically optimized to reach a timing goal or to reach a power consumption goal, for example. Could you envision that something similar exists for side channel leakage? Can we build a CAD flow that allows us to do side channel sign-off? Question number 2 is related to the advantage that you ultimately try to get by having a CAT4 side channel leakage. In many defenses, you need to create, or in defenses, you need to create an asymmetric advantage between the defender and the attacker. And the question is, how can CAT will do that? And if we will have CAT tools, can't they be used in the advantage of the attacker as well? Because now the attacker will understand exactly what you do to deal with side channel leakage. And then third, in the past few years, we have really had a much higher attention to open source, both in the area of IP and cores, as well as in the area of design tools. How will open source tools help us build high quality side channel CAT? So these are the 3 opening questions: side channel, the side channel sign-off question, asymmetric advantage question, and the open source. I'm now going to turn it over to Serge Leef. Serge, you have, would you like to share your screen?
Yes, please.
I will stop sharing here.
Can you please confirm that you can see my screen?
Yes, we can see it.
Okay, great. Patrick, thank you for the introduction, and thank you for inviting me to this forum. So as Patrick said, at DARPA, I'm running a number of programs. I have about 14 programs in my portfolio, and about a third to a quarter of them have something to do with silicon security. And so the way that we think about silicon security is in terms of this reference model. Namely, the attack surfaces that we need to defend are a persistent theme across multiple programmatic efforts that we're pursuing. And so, as you can see, supply chain exposure is one of those things, but there are other considerations that we're looking at. So, for example, in side channel, which everybody here knows what that means, so we simply define it as extraction of secrets through physical communication channels other than the ones intended by the designer. And our assumption in defending this attack surface is the attackers are, if they desire, able to listen to emissions. The second attack surface we worry about is reverse engineering, which is extraction of algorithms from illegally obtained design representation. And once again, the assumption here is the attackers have access to design files. We don't care how they got them, whether it's through delayering or through by somebody walking out the door with a netlist, it doesn't matter. So our strategies are predicated on the adversary having the design files. In supply chain, attack surfaces is another one that we are working on defending, and this is where cloning, counterfeiting, recycling, remarking of chips and representing them as genuine is the issue. So assumption here is the attackers can manufacture perfect clones, and so our strategies all begin with that assumption. And then lastly, hardware trojans, also known as malicious hardware. And here we are assuming that the attackers have already successfully inserted malicious functions into the design, and our strategies begin there. So at the end of the day, what we're doing is we are putting this construct called security engine into the designs, And we are stitching the security engine into architecture and microarchitecture frequently of specific SOCs by advancing the synthesis technology with our partners in the industry. When the security engine is injected into the design, it could have multiple forms and could have significant defenses against one attack surface and minimal against others, depends on the applications and economics of the particular design. But as you can see here, side channel attack surface is one of the surfaces that we care about. And the principal strategy here in one major program is emission reduction. In the program that I just mentioned, we actually have 3 different security engines that are subtly different based on different CPU cores, but they all have cryptographic complex, which contains various implementations of, let's just say, emission-resistant cryptography. So this is something that these 3 security engines are currently being built, and hopefully at the end of our program, they will be readily available through a variety of channels and means. And so basically, to answer the first question, or rather the second question, to us, the CAD strategies here really boil down to 3 strategies. One is emission suppression or obfuscation. 2 is attempt to simulate possible leakages during the design time so it can be mitigated while the design is still in progress. And lastly, analysis of physical representation of the design to respond to accessibility analysis. In other words, what constructs can be visible to various monitoring techniques, and how can they be hidden by rearranging the IC layout. So in the first strategy, the emission-resistant cryptos, there are 2 rather simplistic ways of thinking about building something that's emission-resistant. And one is, well, we can take all the transistors that are active and match them with inactive counterparts, thus essentially making emissions approximately consistent throughout execution. Another strategy is to take randomness and noise and incorporate it into cryptography. So there's too much going on to infer what's happening. Obviously, those strategies have cost. Doubling the number of transistors doubles the area consumed by the cryptographic complex. Introducing randomness consumes a lot of extra power. And so the question boils down to how much of side channel resistivity do you really need to achieve, given that the costs will be present. And once again, it's an application-dependent question. If you're designing an intelligent lawn sprinkler controller, maybe you don't care about the side channel leakage as much as you do if you are, designing a, the smart card or set-top box or a missile control system. The second strategy that we're pursuing is can we, in fact, replicate in simulation what parties like Riscure and Jasper do in the lab. In other words, can we take the expertise that they have in applying post-silicon testing and create a simulation system that would allow designers to essentially run this dynamic analysis and determine if, in fact, there can be leakages predicted at the time of the design when there's still opportunity to mitigate those leakages. And then lastly, we are looking at the third strategy, which is analysis of layout, where you basically designate different structures as security assets. So perhaps a security asset is a register that holds a key, on the chip when it's in plain text. Maybe the wires that connect individual bits of this register to other parts of the complex are in fact security assets as well. All of these things translate into a set of polygons when realized in layout. And then how is this chain of polygons that exist on multiple metal layers, to what extent is this capable of producing emissions? And how can we analyze this during the physical design phase, considering that we have billions of nanoscale structures? And then when and if we do find that some constructs do represent exposure and accessibility, how do we mitigate this exposure? Can we create some kind of shields on layers above or below? Can we change the geometry of an emitting structure? Can we radically change placement and routing to eliminate this effect? If we in fact end up doing that, what do we do to time enclosure? So after time enclosure, if we start introducing all of this security manipulations, what have we done to time enclosure? So there is a concept of security closure, which one of Patrick's questions flirts with, but it is actually something that we are seriously pursuing, the concept of security closure. This is where you would reconcile PPA metrics with security metrics. And so anyway, that's the strategy number 3. And as you can see, some of the threat categories that we're looking at here do in fact represent side channel leakages. And so that's basically my short presentation. I wanted to come back to the questions that Patrick put forth and basically say, yeah, so the first question, our story is security closure is an iterative process that needs to achieve balance between PPA and security. And it is really complicated because this can range from minor rearrangement of polygons to mitigate to replacing, rerouting, everything. And it's computationally expensive because you have to optimize on 4xi in order to include security into this thing. For the asymmetric advantages, defender, attacker, unfortunately, I can only comment on defensive capabilities here. So I'd say that the 3 strategies that we talked about here, emission suppression or obfuscation, functional design time response to leakage prediction through simulation, and physical design time response to accessibility analysis. Those are the 3 strategies that I think are pretty reasonable defense strategies, but you guys are the experts, and I'd like to actually hear if you think these are reasonably sufficient. And lastly, there was a question about open source. Now I have even though I'm investing in a lot of open source EDA and IP, I'm not sure that open source is really in a critical path of serious chip designs. So open source EDA today is largely in use by academics and hobbyists. I am trying to do something more with it and get it to be more mainstream, but that's not the case yet. We are investing in asynchronous design CAD. We have 1 or 2 projects on this, and that also it has capability of producing low emission cryptography. So that's an angle, and that's going to be open source when it's done. But in general, I'm not sure about open source as an interesting narrative vector in this context. Anyway, that concludes my presentation. I apologize if I consumed extra time.
Thank you, Serge. Next, we have Jasper.
Are you able to see my slides and hear me?
Yes.
Okay, good. So real quick, who I am. So my name is Jasper. I've been in security since the late 20th century, to make it sound really dated. I think the most important part of my background here for this panel is that I've been working with industry, government, and academia on determining side channel and fault injection susceptibility, both pre and post silicon. yeah, since 2006 post silicon, and since the last few years also on the pre-silicon side. So I'll go through your questions one by one, Patrick. I won't read it out again, but basically the question here is side channel sign off, yes or no? My answer is yes. I'll give a little bit more detail on that. So when you talk to companies that are producing silicon and they're at the pre-silicon time, they have three main questions. What is my inherent leakage and where does it come from? What options do I have to fix it? And what are the trade-offs for those options? So with inherent leakage, I basically mean that if you design a crypto IP and you do not take care of side channel emissions, you will have leakage. That's just a fact of life that we've established over the last 2 decades or so. And there are there's some public knowledge about where does it originate from within the algorithm, but precise root causing is a non-trivial exercise still. So that's a question that you see, because once you know where the leakage is, then you can start thinking about how to fix it. Now there's a whole body of work in academia, and there's some private IP as well on side channel countermeasures. So there's a number of options that are there, but it poses the third question, and especially if you're talking about side channel sign off, there's this question of PPA. So there's a cost to implementing countermeasures, and for each countermeasure, there's going to be a different cost, and there's going to be some sort of security benefit that you get from that particular side channel. And actually, going for security sign-off means we need some sort of metric around it. So you need some sort of measurable security. And for sign-off, we don't really have something like that right now. So companies that operate in this space, they have sort of their internal standards, or they take a committee of very bright people that say, you know, now we're good enough. But like an actual industry standard does not exist. Similarly, root causing, that's still like a difficult question. But I'm going to focus a little bit on the measurable security part. Because what does that mean? For me, it actually breaks down into 2 parts. So I'm going to start with the right-hand side here, which is measuring the strength of a particular countermeasure. Because basically, if I take a lock and it claims that, you know, it defends against sawing into it, then now how long I'm sawing in order to open the lock, that's a measure I can take. And it's similar with side channel analysis. So these countermeasures, they protect against a particular side channel. I can measure that side channel, look how many traces it takes for me to extract a key, and then I have a metric. What this ignores is the left-hand side of this picture, which is what I call the bypassability. So as you can see here, there's a very nice bike lock, which probably has passed various tests. But as you can also see, it actually doesn't lock the bike. I can just grab the bike and take off with it. So once you start looking at system level security, it's not just about the strength of the individual countermeasure, but also how they cover sort of that entire security space. And this is really hard to measure. So how this happens in practice is basically through human intelligence. So when you do a certification, you go and look at an entire system, you figure out strength, but you also figure out, okay, what did the designer forget, or what are the loopholes that are left? So that's sort of a red teaming certification type of exercise. And in principle, this could also apply to CAD sign-off, but it's not really where we would want to go. CAD are tools, right? It's not a team of experts that measures things. So there's still a very open question there. I think automation plays a critical role there, and also metrics that try to capture, for instance, all side channel signals. Once you capture all side channel signals, this question of bypassability and coverage is basically taken care of. So yes, we envision a general security sign-off if we can figure out this measurable security in this automation part. So for the second question, this asymmetric advantage for the defender over the attacker. So I've been mostly on the attacker side. So that's sort of the role of the company that I work for. And I am not sure that it will give this asymmetric advantage, unless we take some assumptions. Because if the question is as it's posed, sort of the default interpretation of the attacker is sort of the attacker that is omnipotent. Maybe similar assumptions that Serge had in terms of his threat model was like nation state level attackers. Yeah, if you give them the same CAD tools, and you can assume that they have these same tools, you can assume that they get the designs. The defender needs, the argument is again, the defender needs to defend all the leaks and the attacker only needs to find one, right? So there, in that model, I don't think there's an asymmetric advantage. If we sort of constrain the model a little bit more to attackers that have limitations, then you can have interesting discussions on this point. If we take one look at the defender side first, one way where it could help for the defender if a defender is able to fix quote unquote all the leakage. So if there physically wouldn't be any leakage left in a chip, then even an attacker with full visibility couldn't exploit that leakage because it's not there. But that's not a realistic assumption. So I think we also need to assume on the defender side that they also don't have an unlimited budget for defenses. So we will have chips that leak, and then the question becomes how do we make attacks hard enough? And that will depend on the attacker as well as on the defender. So it becomes basically a risk trade-off cost question. So when you look at countermeasures, so on the defensive side, I think what would help to try to get to this point of fixing everything you can is to have countermeasures that are scalable. So you have certain PPA constraints, you have certain performance characteristics you need to meet. How can we maximize security within that budget? If we have countermeasures that are easily scalable, then that means we can just crank them up until we hit the limits. Which is different from like manually designing a countermeasure and then it has a certain fixed cost, which is hard to scale. And then there's just simple risk trade-offs. So if you're more secure than your neighbor, an attacker might just go for your neighbor's target. And this is where it always gets interesting, the discussion. How can we leverage security with obscurity? So cryptographers are, for very good reasons, always mentioning we should not do security by obscurity. But obscurity can be something that actually helps in this cost trade-off. I'll get into that in a second. And finally, I think we should prefer countermeasures that utilize randomness. So even if an attacker knows of that countermeasure, they might not be able to predict the randomness that's used by that countermeasure, and it can still be effective even if the attacker knows that countermeasure is there. So a little bit on security with obscurity. So when you're when we're in the model of an attacker who does not know everything, so who doesn't have the design IP and might not be able to use these CAD tools, attacks are really an iterative process of many steps, many more than I'm doing here. But basically, you acquire a signal, you need to filter it, you need to do some alignment, you need to analyze it, and most of the times at that point you see nothing as an attacker. Seeing nothing basically means we have to just do the cycle again, and we have to try different filters, different parameters, different ways of approaching this. This can iterate for quite a while until you figure out the right set of parameters. So this is the obscurity part. So everything up until finding the right set of parameter is an attacker cost. And if you can increase that to the point where Colin gives up, you know, then at least to an attacker of Colin's profile, sorry for picking on you, Colin, you have resisted this attack. Now, so that's also the reason why you shouldn't rely on this as the only thing, right? Because if there isn't a stronger attacker out there and they publish these results, then the attack effort is again the same as without the obscurity. So yes, I violated Kerkhoff here, but I think for the reason that we are not talking about a cryptographic algorithm. We're talking about a cryptographic implementation for which we really don't know yet how to make it foolproof. Like I think with crypto, we've gotten pretty far with AES, CCC, etc., where the attack effort, even for a nation state, is extremely high. But for crypto systems that include, where the sort of the scope includes the implementation itself, this is one way to protect against lower skilled attackers, not nation states. They will figure this stuff out because they will have the design IP and they will have the CAD tools as well. So yeah, I guess my final answer is a maybe yes. So if we can find these automated scalable countermeasures, then we can at least make it as hard as we can within our budget, within what's realistic. But yeah, let's understand that hiding tools and knowledge from attackers doesn't really help against really serious attackers because they'll find it anyway. I will be very brief on the open source questions because that's really not my area of expertise. But what I've observed is, well, first of all, I think I'm a proponent of open source. I use it daily. Riscure has a mix of open and closed source software, although I would say mostly closed. What I observe is that open source projects are regularly underfunded, as you can see by the quote here. This was Werner Koch, who was supporting PGP. I have to say, after this article, he got funding, but this is a very typical open source question or issue, I guess. I think one really big advantage of open sourcing test tools is that it allows finding more bugs. I think history has shown this over and over again. As soon as Bluetooth test tools became very cheap, a lot of people started looking at Bluetooth and a bunch of issues were found. And as a result, the protocol got strengthened. I think to Serge's point as well, I haven't met anyone who currently trusts open source EDA tools for tape out ready work. So yes, for some simulations and some pre-synthesis analysis, I've seen it, but definitely not going all the way into tape out. So that's it for me. I think we can go back to you, Patrick. Thank you.
Thank you, Jasper.
Let me find out how I turn sharing off.
So next we are going to Colin O'Flynn.
All right, thanks everyone. Hopefully you can see this okay. So I'm just going to concentrate on one quick question, which was how does open source support our quest? Because that's kind of the area I'm in. So I've tried to build basically a business out of doing open source tooling. And I'm going to change it a bit because I'm going to call it accessible tooling, which is something I'll go into. And what I see here is that it's, there's a slight difference between open source and accessible, and it can actually be important for academics. So the difference here is that you do have some accessible tooling already. So when you consider that a fib or really expensive equipment or getting ASICs made, you might say, that's inaccessible, but it actually turns out that it can be somewhat accessible even right now. The issue with it is that it's often closed. So if I'm in Canada, for example, with a Canadian university, I have the CMC microsystems, and lots of universities will have this, right? So they have a similar thing where it's like, I could actually get chips made. It's pretty cheap, right? The government's going to end up paying for it, stuff like that. So in theory, I can get stuff tested and made and compared. The problem that I sort of see in this is that it actually could be less accessible than you think. And the reason is that you run into a lot of issues. And even though this program's been around for a long time, not many people will use it because the one professor is the person who's kind of the gateway to this, and maybe they don't have time to support a student that's interested in it. Maybe the grad student who did the previous work graduated and it didn't get well documented how to get chips ready for this design. And so that's where I see open source really opens that door to accessibility. And where I see that this is going to be very beneficial. So even if we don't trust it, for layout, the ability of open source tooling to open up totally new research is the real value here. So, I think if you say open source tools are going to be an exact replacement for the commercial ones, right, that's a much harder sell. And I don't even know if that's the point of it, right? Because the point of it to me is to have this accessible tooling and resources, which to me means that anyone who's interested in doing the research is actually able to get access to it, right? Because one of the issues with some of some of the closed source stuff might be like export control. It might be the country they're in doesn't have access to it. It might be they're not officially associated with the university. There's lots of reasons that you may or may not be able to have access to it. And normally open source does mean it's accessible. It may not be. So the interesting thing is this isn't always the same thing either, right? So obviously closed source, expensive, you're going to say is not accessible probably. On the flip side, an open source project that's really hard to use, that's not supported, I would say is maybe also not accessible too, because, is a researcher going to use that, or are they going to use grant money to get some proprietary system? So there's sort of an interesting, careful, balance here that's really needed. But what I'm making this claim is 2021, right? Year of, well, Linux desktop, not that. IPv4 is still going strong, but accessible hardware security, we can do that. And the sort of interesting thing you can see is that if you look back at projects that have started, first on the analysis side, this is where a lot of the early sort of accessible, open source, low cost analysis and open source went, right? So OpenSCA was part of the DPA book. I'm sure anyone involved in this area knows. So there was some MATLAB scripts with that helped you go through it. And this is kind of what I learned on, to be honest. David Oswald had this giant, which was a FPGA. So it did some of the hardware side, had some of the software scripts as well. I started Chip Whisperer, and there's been a number of them since then. And they've actually targeted slightly different areas. And there's even more that I haven't listed now. So it's pretty amazing to see these open source tool chains that are highly accessible, I would argue. Many of them, so if you look at Scared by Eshard, JLSC, I don't know how to pronounce that, sorry, Jasper, by Riscure, like there's great documentation and demos that go along with that too. So it's very accessible. But what's sort of newer is that there's also these open source root of trust. So the first one that really took big hold was this Cryptech project. I would argue maybe it was too early because it actually has a lot of cores in there. It's this open source project. It spun out kind of after Edward Snowden discussing the US government, being able to force proprietary or changes to proprietary ciphers. So the point was, let's make a fully open source root of trust. And that project had hardware, had cores, it's still going, but I think it's not maybe as, well known today as it could be. But we've also seen several other root of trust projects launched. OpenTitan, which is run by Low Risk and has a number of funding agents, including Google, is probably the most, I'm going to say the largest. Pretty easy to argue that if you look at the code base, they're trying to target an ASIC target and kind of on the way there. But that's not the only one either that's making pretty big strides. So BeTrusted.io, Bunny's doing this open source project as well as part of a larger open source, trustable hardware push. So there's a sort of root of trust there. Tropic Square is one I'm mentioning. There's no public code, but this was started by some guys doing the Trezor Bitcoin wallet and basically trying to answer this question of having an open source root of trust. But we're starting to get to the point where, right, the question of the accessible tooling actually has real targets that it can use. The final part on open source and accessible that I see as important is actually the ASICs. And this is the amazing thing to me, is that if you haven't been tracking this, is how easily, I want to say, you can actually get chips fat. Because this was always the inaccessible part. This was the real barrier that I saw. And the reason being, I could do it via CMC as a Canadian with the university, but there were so many, a lot of this interesting stuff comes out of independent researchers, and now they can actually do this too. And if you don't understand it, the other part of accessibility, I'm actually, using this course right now to learn one of the process, the zero to ASIC, and you're gonna, in the course of a couple weeks, layer a chip that you can submit to this MPW eFablets wafer, and you can get a chip back. Right? So you can't claim that's not accessible. So that's sort of where I see the importance of open source. It's not a replacement for the proprietary tools, but the fact that, you could do this as an undergrad university student now. You could get a chip back, have it fabbed. I think even a high school student got a chip back already. So that's the really interesting thing that I think is going to come out of the future of open source, tools in this sort of design space. So with that, I think I'll pass it back to Patrick for the next.
Great. Thank you, Colin. So finally, we have Francesco.
Thank you. Let me share my screen. Can you see my screen and can you hear me correctly?
Yes. Yes.
Okay. So thanks, Patrick, for the invitation. It's a pleasure for me being here. And you already introduced me. There is no need to say anything more. I'm probably the most interesting aspect of my research for today is the work I'm doing on automatic application of countermeasure and on the verification of power analysis countermeasure. So we start with the first question. Sign off of a side channel at the chip level. Yes, for me is a clear yes. And to me, the question is not yes or no, it's simply when, because sooner or later we're going to be there. When can be short or can be long, depends on how do we tackle the problem. Probably the simple way to tackle the problem for a sign off of side channel and immediately is to start from what we have studied since more than 20 years, that is countermeasures against side channel attacks. So we start from an algorithm without countermeasure, we start with a countermeasure. We sort of know how to apply the countermeasure because we are doing it since more than 20 years, and then we can sign off that the countermeasure is applied correctly. This to me is the quickest way to arrive to a first initial version of a side channel sign off. Of course, this is a sign off which is similar to what we do with the design of a regular chip. When we have a design of a regular chip and we sign it off, does not mean that the chip works. Simply means that it's very likely, actually extremely likely, that is working correctly. In a similar way, a side channel sign off should not be confused with the ultimate proof of security, but is basically a way to ensure that the chip is more likely to be protected at the end. We still need to do the testing that we are doing already now for a side channel and so on, just we are more sure that we are on the right side, on the protected side. This leads to the fact that we are starting from the countermeasure would lead immediately to the automation problem. The problem of automatic application of side channel countermeasure, that for me it's a must that the CAD should provide. You start again from an unprotected algorithm and with the countermeasure, and your goal is again to have an algorithm where the countermeasure is applied automatically. No need for a design doing a manual process, which is error prone, which can be complex, which may not be exactly in the knowledge of the designer. So automation helps to get chips that are secure against side channel because you have a countermeasure, you have an algorithm, you find a way to apply it automatically, and the result is a chip that is sort of correct by construction when you apply the countermeasure. Again, I stress the point that automation allows you to have a correct by construction of a countermeasure. So very likely, more likely, whatever you want to place before likely, but it's still likely that the things are applied correctly. Still something can go wrong, still we need to verify. Nevertheless, is a huge help towards the direction of a correct application of countermeasure, which ultimately means sign off of side channel resistance and a more secure chip. But why we want this and how? Well, basically, I don't need to say that we need for doing for cost and time to market. Chips has to be done quickly and in a cheap way and secure. We need to handle the complexity of the chip that are getting big and big, but also we want to do this because tools are not designed for security, and optimization that they do can actually cause problems for security. Imagine that you try to add redundancy for whatever, protect against fault attacks or something you need. A tool may think about that this is a stupid replication and can take it away. So we need to address the problem of security within the tools. And I say within because we need to use and to rely, on my point of view, as much as possible on existing design commodity. We have here in the first statement speaking about what happens to time enclosure afterwards. Yes, time enclosure tools now are going to handle it. We need to still continue to use tools that are working for fabricating chip that work. Here I say use as much as possible. I would go a bit more ahead, saying exploit as much as possible existing design commodities. What do I mean as exploit? Well, simply reformulate the problem of security when it's possible, in the same way that the problem of CAD is already existing. For instance, if I needed to identify what do I need to protect and I want to minimize the amount of protection, I typically have to do a partitioning thing, which is part that is sensitive should be protected, part that is not sensitive I can do in a non-protected way against side channel attack. Why this? Because we want to minimize the cost at the end, and there is a cost for everything that we want to minimize. Well, the problem of partitioning exists already, studied already since many, many years, is hardware software co-design. Why don't we simply use the same approach, but we call it protected, non-protected co-design, using the same tools? For instance, this example is simply showing that you want to extend the processor with protected extensions, protected in the sense of side channel resistant. Well, there are many tools that are designed for doing instruction set extension for performance. Let's use it for security. It's same thing, everything is there. Just add an instruction, reformulate your security problem in a form that is understandable and acceptable by an existing tool and try to exploit it. Why? Because the tool is working for such a problem, if you are able to tweak it. So for me, again, that's a clear yes, just when it's the most relevant question. And then you build up whatever you can do with your existing tool. Now, the second question, will designers have an advantage? And I stress the fact that I call them designers, not defenders, because at the end we want to design a chip. We do not want simply to defend. We want to design a chip that is working, consuming little amount of power, work fast, and being secure. So we are designers. Don't forget the holistic view. My answer here is, again, a clear yes. Maybe not necessary, because the CAD will help to specific defend against attacks, but simply because CAD will let designer focus on the problem of countermeasure or defense against attackers and allow them to get rid of the problem of complexity. Now the battle is unfair because attackers has to attack the chip, designer has to defend the chip, but they also have to handle the complexity of the chip design and so on and so forth. Tools are proven to be used in handling the complexity. We see this when it's popping up. This is a processor Z80, and you see the complexity of it. And this is one of the last Pentium. You see the difference in the complexity. Okay, we are able to jump from left side to right side thanks to the automation, basically. A huge amount of the motivation and the reason why we are there is because automation allows us to handle the complexity. Like moving from Stone Age to Renaissance in 1 week, that's a huge progress that we have done in so short amount of time with design tools and automation. Now imagine that you have a tool as a designer that allows you to handle a similar complexity in security. Then of course you can focus simply on defending whatever is not defending by the tool, and then you get an advantage. Again, not necessary because your task of defending against a specific attack is simpler, but simply because you get rid of all the problem of complexity. So the war becomes a bit more fair. And then open source and the quest for side channel. I do believe that is useful, and along the line of what Colin was just saying, open source unlock the possibility for any researcher to do some experiments. You can play as much as you want with open source tool or accessible. I like the definition of Colin, accessible tools, because you can play, you can do experiments, and then everything is there. You basically unlock the possibility of everybody to contribute and to do some useful thing and to play with. It also allows to make a more fair, it also simplify the way of making a fair comparison, because if you have internal tools that are much better than the one that are used on another domain, maybe the comparison is not fair, it's not so easy. So open source open up those things. And again, I do not believe is a replacement for commercial tool, but is a useful thing that allows to unlock the possibility and the potential of many, many researchers. Still, there are some limitations that we need to address. It involves low-level aspect. We need to find a way on how to abstract and how to give low-level aspect available to open source tools. But this is not enough. I think that before arriving to all we want to do with the CAD for security, we need to have a deeper understanding on the problem. So far, I do believe that we are still focusing on a limited niche, one attack, two attack, while we did not tackle yet the problem of composability, how different countermeasures interact among them, if one countermeasure is good for one attack and against the other, and those things. And all those things need to be more understood before inserting them into the tool. In any case, although I say 3 yes, I do believe that our route the route in front of us is quite long, but hopefully we will not get tired of walking. I get back to Patrick.
Thank you, Francesco. So we can now open the floor open for questions. There is a Q&A button at the bottom of your screen. We have already a couple of questions that have been answered and asked. Please feel free to add more. Let me just, there's one I think that I would like to ask to all the panelists, because this was one of the first questions was for Jasper, but I believe that the discussion is interesting in a larger perspective as well. So the question originally was, based on your industrial experience, how much were companies willing to pay for side channel security, particularly interested in the highest cost paid for security in a commodity product? And I would like to ask the question as follows, is how much can countermeasures really cost? What I observe is that if we consider the currently most acceptable countermeasures, and so I refer to Serge's slide from the beginning, they at least double the size of a design at the lowest protection level. And so you're not talking here about something which you optimize. It really is something that increases the design cost to such an extent that you would almost need to take it into account right from the start. And so so the question really is for those of you who have a background in countermeasures, how can we reduce the cost for countermeasures? Or should we simply say, no, let's right from the start say, this is how much it's going to cost. It's just a matter of convincing people that it's just important to have that level of protection.
So Pat, can I weigh in first? I think this is very application specific. So for example, if you have a chip that is for some defense application and the crypto complex consumes 5% of the area, it's actually not a bad value proposition to double the size of that to defend against that problem. It doesn't double the size of the chip, it just doubles the size of a particular portion of the chip. Whereas, per my example earlier, if you're doing intelligent load sprinkler controller, this is not really a concern. So you, even spending moderate amount of money on side channel protection is ridiculous. So I think it's not one size fits all. It's really got to be driven by vertical applications. So and on the other side, if you're going to create random noise, you're going to pay in power. So you're either going to pay in power or in area. And I'm saying these are brute force defense strategies. Now, the other panelists may have much more clever and finely tuned countermeasures that can be inserted and have lesser cost. That would be interesting. But I'm just talking about the brute force strategies, you know, which either result in doubling of the size or doubling of the power. And my point is, it is there, you have to look at the vertical application to determine whether it's required and what's the intensity that's needed.
Thank you.
Yeah, I can add to that. So I think Serge is absolutely right. So this has to do with the vertical application. And in some cases, it's quite clear cut. For instance, in smart card applications, you're not going to put a chip in a bank card without it going through an EMVCO or common criteria certification. And there, we've been talking about sort of PPA costs. There's also a real cost to the certification part of things. And certification is nothing more than having a certain defined level of confidence that your countermeasure will work. And for instance, with common criteria, it has effects on how you do the development of your chip. You need to have certain documentation in place. So the cost is not only sort of the technical, but also just in your whole organization, how you implement it. And then there's a complex area of generic microcontrollers where the manufacturer doesn't know the vertical application yet. There you basically see things all over the spectrum, from no side channel protections to pretty decent side channel protections, and there's just a cost that you pay as somebody using that chip for getting that certain level of resistance.
Great, thank you. Any other panelists? So let me ask another question here that is appearing on the chat. It's a question for Francesco. You mentioned EDA support for SCA analysis is just a matter of when it will happen. What do you think is the quickest path to this? Tools and development, use of existing tools in new ways, whole new tool chains, or others?
I believe is the use of existing tool with some addition, some complementary, let me call it external script or external tweak, which allows you to jump into intermediate file. That's the quickest way in the moment, I think. And then sooner or later will be integrated directly in the tool. So you access to the intermediate file you have, you do something before or something after, you play with constraints of the tool in such a way that countermeasures are not removed, are not touched. And then at a certain point, you need something more, which is abstract correctly the model, the leakage model, and so on so far. But you begin to play with what you have and you extend it. Yeah. Also because what you have is working. You don't want to start from scratch, because at the end, you do not want a secure chip that does not work. You want a working chip that is secure.
So yeah, I don't want to throw cold water on that, but I was a VP at Mentor for a long time before I came to the government, and the question there typically boils down to economics. The big EDA will rarely lift a finger to do anything, even if it is to expose an API to something, unless there is a business reason to do so. And business reason could be a mega customer is demanding this, or many customers start demanding something. And so one good example of this is what the synthesis tools today do to security. They essentially optimize it out. Essentially, they're not sensitive to the kinds of things that we want to put into the designs, and as a result, they work against us. So the business drivers, in my opinion, are not there today. The customers are not requesting addition of this type of capabilities or features, or the customers that are requesting it, they don't have economic power to be influential. So in the programs that I'm doing with the big EDA, I am actually influencing / requiring them to do things that would, for example, make synthesis not destroy security structures that are being put in, or expose interfaces through which researchers can add novel security-related capabilities. But without money talking here, this wouldn't happen.
Thank you. Jasper, Colin.
I like Colin.
So, okay. Oh yeah. So did you want to add to that, or shall we? Can I take another
No, let's
question?
go on for me.
Okay. So I noticed in the chat there are several questions which are sort of similar, and since we have experts here on the panel, I would like to ask it to all of you. The questions seem to ask like, well, I'm interested in this open source EDA tooling or developing EDA tools. I'm interested in countermeasures, but really, what is my starting point? Where can you learn about countermeasures, and where can you learn about EDA for EDA for countermeasures? What would you recommend that? I know there's many students on the panel here. What would you recommend these students do? Does that make sense?
Yeah, I think this area has been sort of a dark art area, and so when I have questions about this, I call Jasper. Get to know Jasper. That's my answer, maybe. I think it's a good question. Maybe somebody from academia can weigh in on this as to whether any kind of coursework is offered in this area. That wouldn't be. I wouldn't know.
We don't have any Rambus lawyers on, do we? Be careful.
I avoided answering the Rambus question, so.
I'm in Canada. I think I'm safe. Yeah, I think one of the interesting things, so actually, and this was maybe a bit of a question for the other panelists, is you see a lot of people doing FPGA implementations, which is a really good way to understand this, because I linked to, so for example, we use this Cryptech Alpha project, as it has a number of course, ECC, AES and stuff, and it's all open source. If you're interested, because you can kind of break some of those, we've made some tutorials that are open source saying, you know, here's how you break it, because it's pretty tricky to apply generic countermeasures without doing the analysis first, which is, I think we're all, you know, it's coming back to this whole analysis of the leakage and finding that leakage. If you have the FPGA experience, I think that's pretty interesting. What I don't know, and this would be a good question for other panelists, would be what, you know, how do countermeasures work that are specific to the ASIC design? Because there's obviously so much you can do on an FPGA. You're always using sort of standard logic implementations. So I don't know, you know, how that maps if you want to try to do like balanced rail stuff, if that's even possible to emulate in an FPGA. But there are resources as far as breaking the devices, which I think is a good spot for students to start out. But I'll let other people chip in on the second half of that.
Yeah, I agree with Colin. So start for people on the hardware side, start with an FPGA. For people more on the software side, take a simple microcontroller. And you know, Colin's tools are great to do some measurements. There's also other low-cost options. If you, yeah, side channel is, and especially what I've seen in my experience is, if you come from it only from the designer side, you will come up with a great countermeasure that doesn't work. And I'm not trying to downplay your skills here, but this is just what I've seen over and over again in industry. You know, a company comes to us, they've designed this countermeasure, we put it under an actual measurement setup, and the first time the thing leaks like a sieve. Unless you already have, you know, 5, 10 plus years of experience in designing these things. That's just what commonly happens. So take some easy targets, do some measurements, and then start building your own countermeasures and see how the leakage changes. If you don't have access to hardware, I think there's less you can do, of course, in the interactive space there. We are working on, as Serge mentioned earlier, simulation type approaches where we simulate a hardware design and then look at the leakage there. I don't know, in Colin's words, how accessible that is to most people out there. There's all the, this is being recorded, so all the pointers that Colin gave in terms of open source side channel packages, those are good to look at. Usually they will come with some traces or some examples that you can play with and really get a sense of what it feels like to do these attacks.
Great, thank you. Yeah, these are all great pointers, and it's very useful for the audience to be aware of this.
If I may, I think that what you said is quite important. Begin to play with what you have available. FPGA is definitely easy reachable. Microcontroller is also easy reachable. You have many publications that are now accessible without any problem, and also some countermeasure, and part of those tools starts to be published as open source. They are available. In any case, you can always contact the authors of a paper you believe in it's relevant and ask if they can share something. Most of the time, the answer is yes.
So closely related to that, could I ask what if you believe that there's a need for benchmarks? When you look at the typical side channel literature, you see that people are attacking AES over and over, but AES is 20 years old. We are moving to new cryptographic algorithms. We're moving to post-quantum algorithms, which have their own models. Isn't there a need for some good benchmarks as well?
I strongly believe that there is a good need for a benchmark. This part of the fair comparison that we need to have. We need to have a meaningful pool of benchmarks. Most of us is just using AES or simple block ciphers because they are representative enough. They are easy to be used. We know the model behind more or less in a certain way because of the age we are studying them. But still, the benchmark is a problem that in our community is not solved. And we have seen that there are experiments where it's not exactly what you asked, but like if you think about the open available traces, as soon as they started to be available, this showed that there was this result in a very relevant impact, because everybody was able to compare fairly different metrics, different approach, different way to classify the traces, template attacks, and so on. So we certainly need more advanced and more appropriate benchmark in our field.
I would add to this that beyond benchmarking, I would be interested in metrics or estimations that you could use to evaluate relative goodness of defense strategies. So as I'm investing a lot of money and effort into system optimization, I would like to be able to do things that we do for power, right? So to truly compute absolute power dissipation, you need to go all the way to polygons to really have absolute measurements. However, it is possible to do power analysis to determine whether architecture A is better than architecture B. Okay, and that is what we need to guide the optimization. I would be very interested in something like that for side channel leakage assessment. In other words, can I quickly estimate relative being the operative word, goodness of one architectural solution versus another? And maybe I need to do this at RTL level or gate level, where actually very little, if anything at all, is known about physical implementation. So that would be very valuable as a driver for optimization.
Definitely. Every time that you want to do something automatically, you need a metric to instruct the tool. And that's that's probably one of the major problems we have in our domain. The metric is so limited at this point. When I say limited, is we have metrics eventually only for at least mostly 99% for power analysis, but that's not the only side channel. So metric is.
But I think, Fran, if you walk away from this concept of I need to absolutely deterministically measure what this number is, if you walk away from that and say, okay, I'm willing to accept relative measurements, I think the problem becomes a little bit more solvable, though I would agree with you, it's not yet solved.
No, I also agree that you need to go away from this problem of absolute correct. And my goal is to have a chip that is very likely to be secure. I cannot have 100% assurance. So if my goal is having a fully secure chip after a check an RTL, I'm out of the scope.
So yeah, the whole 100% assurance thing is, of course, impossible to ever say. But when I deal with my customers in the military, and I can tell them, we think it'll take adversary 2 to the power of 106 years worth of trials to penetrate this, they almost are ready to accept that as relatively secure. But I can never say that with 100%. So you have to translate this, as Jasper pointed out, into effort. If there's a certain line where you lose the economic attackers. When the effort increases to a certain point, it just doesn't make sense. But for nation states, that line is drawn somewhere way out there. If they think something is really critical for them to access, they will invest potentially infinite amount of energy, time, and money. So like I said, the line is drawn in different places for different use cases.
Right. Thank you. So we are close to the end of the panel, and I would like to first of all thank the panelists, but I would also like to offer them a minute of closing statement. We have many unanswered questions. I'm very sorry to the audience that we could not address all of the questions, but they are, so the panelists can see the questions. If you would like to answer them by typing, please go ahead. And let's start with closing statements. Who would like to go first? I'll leave the order in the way you would like, you would prefer it.
Well, I mean, I'll jump in since I was the first to speak. So I just wanted to say one thing. We've talked about open source here quite a bit, and the way I sort of think about open source is, can this turn into viable, scalable, growing business that real people use to design real chips? And to me, thinking about open source in a horizontal fashion is somewhat flawed, because you would have to take on the big three EDA, which have each of whom has 2,000 to 3,000 person sales channel. And even if you had the best technology in the world, you cannot really easily succeed in that space. I do think that the promise for open source exists in vertical application spaces. So for instance, if you take a problem like, let's say, one that's near and dear to my heart, signals intelligence, which actually translates into commercial problems like smart cities and sensor aggregation and so on. It is possible to put together high quality open source design system for that domain. And there's absolutely room for an opportunity for side channel resistance solutions in that space. So in my opinion, there are opportunities for open source. It is pivotal to develop a business model that's viable. And I would look at Red Hat and what they did, which is charging for support subscriptions, but keeping things open source. So I think there are opportunities for open source in vertical markets. And in those opportunities, there are plentiful opportunities for security. And I don't want people to interpret my comments about open source as negative and pessimistic. I'm just saying that a realistic way to think about proliferating open source is through verticals. That's my closing statement.
Thank you very much.
Well, let's stay in order then, and I'll I'll go next. So I think from my end, CAD is going to be the only way to solve this problem at scale, or at least some sort of automation around mitigating the side channel issue. And I think I can point back to Francesco's excellent remark that we're not talking about defenders here, we're talking about designers. And designers are not people who are security experts. We've tried that route, training them to be, understand side channels and everything. It just doesn't scale. And people still make mistakes. People are people, and that's not going to change in any case. So I think some sort of automation is required. Together with DARPA, a few partners, Riscure is working towards this. We're chipping away at the problem. I see solutions on the horizon, but we're definitely not there yet. I think in terms of the economics, you see that the fact that we're having this panel, side channel, and for that matter, faults as well, they are just becoming a more and more important part of the threat model. I recently tweeted that fault injection only becomes part of your threat model when you've been hacked with fault injection, and this is just starting to happen all over the place. So yeah, I think it's getting more important. I think that will bring the economics. I guess I'll close with thanks also to everybody being here, being interested in this topic. I'm looking forward to all your creative solutions in this space. And with that, I'll pass it on to Colin.
All right. We solved the problem, Patrick. So yeah, thanks everyone again for the panel and attending. I guess Jasper and I should push our book that Patrick was a reviewer for too, if you're interested in getting started. And I'll post into the chat here actually those other open source projects I mentioned. And I think the thing to me that I think is really interesting is seeing what people can do when this becomes more accessible. So I really think, you know, we're starting to see side channels becoming pretty common, and is, in my view, in that people know about it. When you go to like Black Hat, it's no longer this weird thing that's like, oh, like, how do you do that? There's a lot of, you know, more commodity, I would say, attackers that are using it as part of analysis, and where there is financial interest, like automotive tuning even, right, is something that's coming up again as using these more advanced attacks. So I think it'll be really interesting to see where this goes, to see where the sort of, you know, automated analysis can take it, and especially where the potential to actually have customers caring about it. Way at the beginning, that was one of the big issues, was customers didn't care, so they didn't want to spend money. So, you know, it's a slow trickle process, and people like DARPA that are able to sort of, you know, skip that slow process, I think will be really important in the future.
Thank you.
So I answer with 3 yes to the questions that Patrick gave us, because I do believe that is the direction to go, and we definitely can reach, but as all of the panelists confirmed, including me, we are far from there. So it's a great opportunity for everybody, from for academia to do some interesting research in the topic, and I'm happy the students are asking questions about it, because it's always good. I'm also curious to see what Colin said now, if the things get more accessible, what's going to happen in the future. But I also do believe that there is an economical value behind it, as we have seen in the past when started to happen design automation. We had seen also the rise of startups doing design automation tools. I'm expecting to see the same thing for startups that do design automation for security. So I do believe that there is an economical opportunity to not only research interesting opportunity for a very cool and relevant problem. And I would like to thank all the panelists for the interesting discussion, and the organizer and Patrick for the invitation.
Great, thank you, Francesco. So this concludes the panel. I would like to thank, first of all the panelists for the excellent interaction, as well as the audience for the many questions. And then finally, the SIDA, of course, for organizing the panel. Swarup, if you're still online, then we are ready to wrap up. If you want to close.